It's a great pleasure to be here to talk about one of the things that we all get excited about as programmers. So thanks for your time. Really looking forward to interacting with you this evening. So I want to talk about lazy valuations and how it has an impact on efficiency. And so I want to first start talking about what does it really mean to be lazy? Well, when it comes to program evaluation, we always want to know when a certain instruction gets evaluated. Well, most of us have been programming in imperative style of programming. And in imperative style of programming, we do mostly what's called eager evaluation. So eager evaluation is when we evaluate things as soon as we get to the instructions. Well, it turns out being eager is not the right thing to do all the time. In fact, both in life and in programming, it's actually good to be lazy. And so we'll talk a little bit about what does it really mean to be lazy. Well, in terms of that, I want to talk a little bit about how applications or functions are evaluated. Well, we talk about what's called an applicative order versus a normal order. Most of us programming in imperative style languages, mainstream languages, have been using what's called applicative order. And the word applicative order actually makes a lot of sense if we think about applying a function, where you're calling a function. So let's talk about a little example and see what that really means. So let's say for a minute, I want to create a function right here. And let's say this is going to be called as a function called add. Let's keep it extremely simple for now. And I'm going to have an operand 1 and I have an operand 2 in this case. And let's say all that this function is going to do is simply return operand 1. And of course, plus operand 2, it's going to return as a result right here. Well, that's great so far. I want to have another function that I want to call right here. And this function is going to simply return, in this case, just an integer. And we'll call it as evaluate. And evaluate is not really doing much at all, except it takes a value. And in this case, it simply is going to return the value that it takes. So again, pretty simple so far. But I want to come back here, and I want to print out the result of calling evaluate. I want to call add with the 1 and 2, let's say. Well, when I run this code, of course, it produces a value of 3. Nobody here is surprised about it. But the question is, when does add 1, 2 get evaluated? And that is also an answer everybody here is absolutely familiar with. Well, of course, the program is going to first call add, take the result of add, and then it's going to pass that into the evaluate function. So that makes really good sense. So that's pretty obvious to everybody in this room. Well, we call that applicative order. So applicative order is the order of this evaluation is in the order in which you apply these functions. And that's what we've been doing. And we may even wonder, hey, why do we even talk about it? Is there a different way to do this? Well, let's give it a try real quick. Now, in this particular case, of course, we know that add is being called first and then evaluate is being called. But let's entertain this thought just a little bit. I'm here in Haskell, and I'm going to call add, let's say a and b equals a plus b. I got evaluate, and I'm going to say given a value, return a value. And I'm going to say main equals, in this case, of course, I'm going to call the print function, call the evaluate, call the add function with 1 and 2, run the code. Sure, it produced the same result. But I want to ask the question, when is add 1 and 2 being evaluated? Well, the answer is not that obvious anymore. It is not going to do what Java is going to do. Now, of course, you may wonder, what is it going to do? Well, this is called a normal order. Well, the word normal is actually abnormal. We don't really see this too often. So it's kind of interesting that we call it normal order. But let's entertain the thought why we really want something a little different. Let's go back to this code for a minute. And in this code, of course, I'm going to say add called. And you can see pretty clearly add was called, so no doubt about it. But I'm going to do something a little different. I'm going to change this evaluate to return a 42. Now, I call evaluate, pass it a value, and what does the evaluate function do? It takes the value and says, nice value, discards it, and calls 42. So now the question is, would add be called or not? And the answer is yes. Let me change the question. Do you think add should be called? That's a very different question now, isn't it? Well, if you care about efficiency, you would say, why in the world do you want to do all the work of calling add when the result of add is being discarded entirely? So if you notice, when I run this code, you can see sadly, it did call add. But that's a waste of effort, because what it did was it ran add, and imagine add is an expensive function. It took all the time to evaluate it. Only at the end it said, thanks, but no thanks, throws it away, and then returns the number 42. That's such a waste. Let's retry this again, but let's go back to Haskell. Well, unfortunately, I can't do the same thing in Haskell and show you, because Haskell is pure, and I can't put a print statement. If I do a print statement, it'll immediately complain saying, what are you doing? You're making this function impure. So I got a little different way that we can explore this. So let's get back here to our command prompt for a second. We'll just break through this a little bit. And I'm going to bring in the GHCI, which is the REPL, and I'm going to ask it to load this sample.hs file. So I've got it right here. So once I loaded the file, I'm going to put a breakpoint. I'm going to put a breakpoint on line number 1, character number, it's going to be 16. So I asked him to put a breakpoint. Now I ask it to call the main function. Now sure enough, you notice it is waiting in the function, eager to evaluate that 1 and 2. I say, okay, thanks, continue please. So you can see that it's producing the result of 3, which is exactly what we expect. However, let's get back to this code and do exactly what we did here on the other side, where I'm going to just return the value 42. Well, in this case though, Haskell did not really call add method at all, add function at all in the first place. When you said add 1, 2, Haskell says, yeah, eventually, no rush, what's the hurry? What are you planning to do with it? I'm going to call evaluate, can you run it? It says, maybe. What do you plan to do with evaluate? I'm going to print it. Okay, that's a good reason. I'll go call evaluate. You go into evaluate, hey, what are you doing with the value? Nothing. Well, good, I didn't really waste my time running add. So it never actually runs the add function, it simply returns 42. Let's make sure that's really true. It runs 42, it returns 42, but let's go back here. Let's load the file one more time, sample.hs. And now that I have loaded it, I've got a breakpoint on line 1, 16, just like before. But this time though, I'm going to call main, and notice it never ever stopped within the add, because it never had a reason to get into it. It's that lazy. So you can see how the language behaves very differently here, and the reason for that in this particular case is this is called the normal order. So in other words, Haskell says, I don't have a reason to evaluate add right now. I can postpone and run it whenever it's needed. Now we cannot just make an arbitrary claim that normal order is better than applicative order. Like everything else in life, there is pros and cons to things. Sometimes applicative order is really good. Why? Because it evaluates once and reuses the value several times. What if this function was called multiple times within the other function? You don't want to really reevaluate it. Well, on the other hand though, an applicative normal order may trigger evaluations inside the function, but other techniques come into picture. For example, languages are capable to memorize the results, so they may really be clever to say, hey, I just called this function, I don't have to reevaluate it. So eventually the efficiency may kick in a different way. So it's really hard to say arbitrarily which can be better. But I have a hunch that really normal order can really be a little bit better in terms of one aspect at least, it is to be lazy. So I'm going to say some languages are naturally born lazy. They're just sitting there and drinking soup, doing nothing really, right? And they're all just happily hanging around on the beach doing nothing. Some languages have to work really hard to be lazy. You got to put in an extra effort to be lazy. Well, we saw this example here in Java. You saw this was actually eager evaluation after all. But let's entertain one more thought before we go further. Let's say we are here in Scala, and in Scala, of course, I'm going to define the function called add, just like we did, op1, which is an integer, so I'm going to define op1 here. I'm also going to define op2 here as integer, and of course, in this case, I'm going to simply return, let's say op1 plus op2. But before I return, well, Scala is a hybrid language, so it doesn't prevent us from doing stuff like impurity. So I'm going to go ahead and print out here, let's say add called for a minute. Now, of course, I'm going to call, in this case, evaluate. And evaluate takes a value, which is an integer. It simply returns the value. And finally, I'm going to simply say print line evaluate. And we will say add of 1 and 2. And we'll do exactly the same thing here in Scala like we did in the case of Java. Well, you can clearly see that it did call add. But I'm going to go back and change this for a minute, and I'm going to say 42 here. What do you think? Is it going to call, or is it going to remove it? I hear nods that it's going to call. How sad it is. It did call it, right? So it's not that efficient. It doesn't look out for it. But is that a lost cause? Let's get back to this in a minute. Let's go back to a slightly different example. Let's take this add function one more time, but let's work through a slightly different example. Let's say we have an int value equals, let's say 4. And I'm going to say if value is greater than 5 and add of, let's say 1 and 2, then I'm going to say, well, let's go ahead and output, let's say result. And of course, else, I'm going to simply say output, will say no result. Well, okay, so this is again Java code, and I have a 4 as a value, and I said value is greater than 5, and add is 1, 2, then print the word result, otherwise print no result. What do you think? Is it going to call add, or it's not going to call add? It won't. And what's that called? Come on, you know this. Don't be shy. That's correct. It's short-circuiting. So everybody knows short-circuiting, right? And when you program in languages like Java, you plan for short-circuiting. You know that if the first parameter evaluated to a false, and you have an AND operation, the rest of the code wouldn't even run. You also know that if the first is a true, and you have an OR operation, the rest of the stuff won't run, and we have kind of gotten used to it. So when I run this, of course, what's going to happen? Oh, of course, I got to check for the proper value. Let's say in this case is greater than 5 as well. Well, in this case, you can see that it's not going to reach to add at all. Yay, that's awesome. Well, that's pretty good, isn't it? Let's do the same thing here in Scala for a minute. So I'm going to say in this case, define a value. Let's call this as value equals 4. And I'm going to say if value is greater than 5 and add of 1 and 2 is greater than 5, then I'm going to print, let's say, result. Otherwise, we will simply say else. We'll simply print out here no result. So exactly the same code. Well, when I run this, of course, you can see it did not call add. Life is good. But I want to do a little bit of a slight change here. I'm going to take this call right here for a minute, put a little temp in this case, and then I'm going to say int temp is equal to that. So I stored it away into a temporary variable. Much like that in the case of Scala, I'm going to say val temp equals add of 1 and 2, and I'm going to simply go ahead and pass the value temp right here. So we could argue both these code are, after all, equivalent, and it is, logically speaking. But when I run this code, what do you think? Is add going to be called? Would you want add to be called? No. So again, it's pretty sad. We did all that extra work when we don't have to do. So in other words, a minute ago, add was lazily evaluated, even in Java, because of short-circuiting, but here it's being evaluated eagerly. And generally speaking, I'm beginning to realize as I'm getting older, eagerness is not such a good thing, even in life as in programming. Sometimes it's good to just sit back and relax and say, let life happen, right? Well, in this case, of course, we rush to implement and execute it, only for it to be thrown out. What a waste. Let's get to Scala. I know some people are holding hopes for Scala. What do you think is going to happen? Yes, it's going to run, or no, it's going to be smart and not run it? Run it. Okay, no confidence here. Well, you're right. It did run it. But that's really not fun at all, isn't it? But you have to work a little extra, a little hard, and you can tell Scala politely, hey Scala, why don't you be just a little bit lazy, please? So you can ask it to be lazy at times, and when you say lazy evaluate, it's more than happy to not run the call. So you can, annotate, if you will, variables as lazy. So what's happening at this point? Notice without the word lazy right now, you can see that it evaluated the add call, but I added the word lazy, and it no longer runs it. So Scala says, oh, you said temp is lazy, so I will postpone evaluating this until you actually make use of the variable. And if you never even asked for it, I would not bother to evaluate it. So that seems like a great idea. Well, then the obvious question people normally ask me is, gosh, if Scala is smart enough to do this on request, why can't Scala do this all the time? Well, why can't they just make everything lazy? Why can't that be possible? Well, the reason is, this is where we have to keep in mind a few other things that interplay quite often. When you're dealing with functions, there is something else you need for laziness. Laziness is not something that is too easy. It requires a bit of a discipline. And maybe surprising you, because usually when somebody is lazy, you say that person is irresponsible, call them a bum. But actually it turns out to be lazy, you really have to be smart. And so to be lazy, there's something else that's needed. And that is, your functions cannot be impure. Well, you cannot really introduce impurity in functions if you plan to be lazy. In other words, lazy functions cannot have side effects. So what does that mean, lazy functions don't have side effects? Well, if the function were to have side effect, let's look at an example. Let's say your boss calls you on February the 1st, and your boss says, I've got a very important report due for you on April the 1st, very appropriate day, right? And your boss says, I want you to promptly work on this project and get me the report on April 1st. What would you actually do? You would start it very promptly on March 31st, wouldn't you? Right? Seriously, right? I mean, why would you do it any sooner? In fact, if you know you're going to quit on March 15th, there is no way you're going to start it on anytime sooner, right? Because, heck, I'm going to be quitting. Why would I want to waste my time doing this stupid report? But then there are some bosses who are really annoying. You know who these bosses are, right? They tell you the report is due, the final report, as they say, is due on April the 1st. But I want a report from you, interim report from you, every Friday. You're like, damn. Now I got to work every week, right? Well, in the first case, you can be absolutely lazy because nobody has a clue what you're doing until the time the report is due. But if you have to produce a report interim every week, that means there's a side effect. Other people can see what you do along the way, which means you cannot be postponing it. So that's exactly what happens with code as well. When you execute a piece of code, if the code is absolutely pure, well, guess what? It doesn't matter whether you run it now, whether you run it later, or you don't run it at all. Nobody cares because they only are after the result when they ask for it. But if the code was producing a side effect, like writing to a log file, printing to a console, coming to a database, well, the world will know whether that code ran or not, whether it ran now or it did not run or ran later. Well, you cannot be really lazy. Well, here comes the problem. Scala is not a functional programming language. Scala is a hybrid functional programming language. Almost every language you come across today that was mainstream or trying to be in mainstream have really embraced two mixed paradigms together. In Java, for example, in C#, C++ even today, you can actually do imperative style of coding, but they bolted on functional style of coding to all these languages. Scala especially was created as a hybrid language from the get-go. So in Scala, you could write imperative code, or you can write functional style code. But anytime a language supports multiple paradigm, when they're hybrid, when they're not pure, they have to really work with the least common denominator. If the language arbitrarily assumes that every function is pure when it's not, we're going to be in trouble. On the other hand, language like Haskell is really developed in a very different mindset. In the case of language like Java and Scala, you have to make a plea. You got to request and say, please, can I be pure here? In a language like Haskell, everything is pure, and you have to work your way hard to make something impure. In the case of Haskell, that's why we said do here. Or you probably have seen things like IO, which I profoundly call as impure operation. You are marking functions to say, could you please give me this ticket to be impure here? You're getting a pass to be impure, a little dirty in that particular function. So you cannot really have impurity in functions like add or evaluate because Haskell demands, it doesn't assume, it demands that functions are pure by default, except for functions which are not pure by way of expressive consent that you have gotten. So that tells us why you have to really work a little harder in these languages because they favor impurity by default, whereas languages like Haskell favor purity by default. So we talked about the eager evaluation versus lazy evaluation. We also talked about how to really promote laziness. But if you really want to postpone evaluations, there is yet another way to really become lazy. And that is through lambda expressions. So let's take a look at another example here for a minute to see how we could potentially become a little lazy. I've got this little add function on our hand. So I'm going to say at this point, let's say int value equals add 1 and 2. And I'm going to go ahead and just do that for a minute. And then I'm going to say done for a minute. So we'll just say done. And you can see in this case, it did evaluate that and then produce the done. You can see the output at this point. But this is eager evaluation. It ran right away. But I can do something a little different at this point. Rather than calling the value here and calling the add and assigning the value, I'm going to make a slight change to this function. I'm going to bring a functional interface here in Java. And in this case, I'm going to turn this into a supplier of the value. So I'm going to say supplier of integer, and then I'm going to say value equals. And this time, however, notice I've created a supplier. Now, what does the supplier really do? Well, the supplier says, I am going to provide you a value, yield a result whenever you call. But one thing about supplier is it takes nothing, but it's always eager to give you back something. So I call supplier as its mother's love. She never wants anything from you, but she always is ready to give you love, right? So supplier is kind of like that. It's always willing to give you something without anything in return and expecting anything. What a beautiful interface this is. So this interface says, just call me when you want to. I'm going to return a result for you, right? Well, in this case, when I run this little code, you can see that we did not really evaluate that function. We got laziness automatically with lambdas. Of course, if I were to go back here and say value.get, you can see that it's going to invoke the value because you're exercising the lambda. So essentially, what a lambda does is it helps you postpone evaluation. So you almost get laziness for free when you use lambdas. Don't assume lambdas are always lazy. Lambdas could be eager, depends on what the function you call does with the lambda you send in. They may turn around and call it right away. Then obviously it's going to be eager, but it could postpone and evaluate it as well. Well, given this, let's talk about how we can make use of some of these wonderful laziness in our code. Well, what if I want to do certain operations in my code that can become a little bit more intense in terms of operation it performs, but we want efficiency in code? How are we going to really get it? Well, to understand this, I'm going to take a list of numbers, but notice the sequence of numbers I have on my hand. I've got a 1, 2, 3, but I changed the order 4 and 5, followed by all these other numbers. So you got this 1, 2, 3, 5, 4, and all that. I want to write a piece of code here, and the code I'm going to write here is going to say, return the double of the first even number greater than 3. Well, you know how to write this code in imperative style. But what would you do? You would start with result to begin with, set a value of 0. You would say result is going to be what you're going to print out. You could say given an element coming from numbers, you could say if the element is greater than 3 and element mod 2 is equal to 0, then of course you want to say result is equal to element times 2, and then you want to break out of this. Well, clearly this is an imperative style code. Almost everybody here has written this a million times over. And if you run this code, it says the result is 8, so there is not much surprise in this code. But I'm going to ask you, is this code correct? And you can imagine right now, your brain is going through processing where you're saying yes, no, right? And this is really confusing you. And in fact, I love this example because what I normally recommend is put this code in front of somebody, but sit in front of them on the opposite end of the computer and watch their eyes and how they're going to read through this code. And the eyes would go like this. And then it would come to this point. That's called the point of confusion, right? Because you're like, is it correct? Well, actually, this code is broken. And it's broken because of certain reasons, and we don't even see it yet. But we will write this in functional style and see the benefit of that right away. So I'm going to say output, and in this case I'm going to say numbers. So we'll start with these numbers, and I'm going to get a stream. In this stream, I'm going to filter, given an element greater than 3, and given an element mod 2 is equal to 0, and then I'm going to say perform a map operation of element times 2 and find first, and once you find the first value, give it to me. Now when I run this code, you can see the result is not 8 but an optional 8. So now you know the problem in the previous code I showed you. It always gave you a result. What if the collection was empty? What if the collection was not empty but had no even numbers at all? What if the collection was not empty, had even numbers, but nothing greater than 3? In all those 3 cases, it gave you a result of 0 when the result is actually, I don't have a result. So this code was not giving us the right result. It was actually waiting to fail and hurt us. And on the other hand, this code is very innocent and very revealing. It said, you know what? I'm going to give you an optional because there are times when I may not have a value for you. So you're doing a preemptive strike and handling that situation right away. Well, so there's already a good news about this code. It's a lot better. But you look at this code and say, wait a minute. I know what this code is going to do right here. We can look at the performance of this code. Given this example of these 10 values, what is this code going to do? It's going to perform the following computations. Remember short circuiting, right? So it takes every single value in the collection. Is 1 greater than 3? No. Is 2 greater than 3? No. 3 greater than 3? No. Is 5 greater than 3? Yes. Is 5 even? No. 4 greater than 3? 4 even. Double 4, break out. That was 8 computations. So that was really awesome. The result of this was it performed 8 units of work. Not all the units the same, but nevertheless 8 units of work. Now obviously, when you want to program in functional style, the first thing you're going to look at functional style and say, that's beautiful. You're going to look at functional style and say, that's cute. But as programmers, we have learned something else to ask along the way. You ask, what's the catch? Right? What's the cost of doing this? You're not going to take something home because it's cute if it's going to be a maintenance problem, if it's going to be expensive. So if I tell you, hey, this code is so cute, you're going to only pay 4 times more price to run it, you're going to say, could you please get out of here, right? So nobody's going to be interested in a code that runs slower just because it's cute. Well, let's entertain this for a minute. We got a collection of 10 values. I want to know if each of the values are greater than 3. Well, how many operations would it be if we do this eagerly? That's 10 operations. And last time we checked, 10 is greater than 8. It's already dead on arrival. But let's add insult to injury. What about this one? It's going to take values greater than 3. That's 7 values. 10 plus 7 is 17. Well, I got 4 even numbers in the value. 4 numbers doubled. 17 plus 4, 21 operation. Gosh, this probably is 21 units of work. Well, actually, if I go back to this code and say 11, 12, and keep on going up to a million, what's going to happen? Well, this code, of course, is still going to do 8 units of work in this example. While this one is going to doing, I don't even want to compute that right now, right? So that would be really shameful if we went that route. But thankfully, that's not true at all, thanks to lazy evaluation. But before I talk about it, I'm going to go back and change this code just a little bit so we can understand how this is going to work. So I'm going to go back here and say public static, let's say Boolean, is greater than 3, and I got the number on my hand. I'm going to say return number is greater than 3. I'm going to go ahead and do that for the other 2 also, is even, and I'm going to return a mod 2 is equal to 0. And then finally, I'm going to say int over here, and let's call this as double it, and I'm going to return number times 2. So all I did was I wrote these little helper functions. Now what I'm going to do in this code is I'm going to say sample is greater than 3. I'm just minimizing the effort to make changes to this code a little bit later. And I'm going to say in this case, it's going to be is even. And finally, I'm going to change this call to sample double it. And of course, when I run this, it still produces the same exact result. However, notice I used stream here in Java 8. Well, there's a reason why Java decided to introduce the word stream rather than just putting filter and all that on the numbers directly. And the reason is a collection is eager in Java, but a stream is not. So what does a stream do? Well, I'll explain what streams are. And there's one feature of stream that I've only seen among my children. They both are lazy to the bone. I'll describe a scenario I often have seen in my house, and this will help you understand how streams behave. So my dear wife would look at my son. He's a teenager, so you know what I'm talking about. So she would look at him and say, I want you to turn off the TV. It's as if no words were spoken. And nothing happens, nothing moves. You know that feeling if you have teenagers, right? And then she would say, I want you to throw the garbage out. And nothing happens. And then she would say, I want you to finish your homework. Nothing happens. And then she would say, I'm calling daddy. Everything happens. So the point really is, all those calls were accumulated lazily. And the minute this word, I'm calling daddy, is triggered, immediately, what do you want me to do, right? Everything gets done. Exactly the point. You go to the stream and say, hey stream, filter, filter again, okay, map, whatever, find first, oh dear, let me get this done. So there are two kinds of functions that you have on your hand. These are called intermediate operations, and essentially these are lazy, and this here is called the terminal operation. So a terminal operation is an operation that gets evaluated only at the very end of the sequence. Everything before it is lazily evaluated. So in other words, what does this really do? Well, essentially what's going to happen here is, when you make this particular call and you go to the stream and say, hey stream, I want you to filter. It doesn't really move its muzzle. It doesn't go do any processing. Instead it says, oh, so you gave me a function, thank you. And it simply says, I'm going to hold on to this function, and that's all I'm going to do right now. Then you come to the next line, and you say, filter again. It says, okay, and all it does at this point, it simply attaches these two functions and says, I got a little pipeline waiting for you. I'm not going to do any work, but this is pending request. And of course, now you call the map function, assuming I have another marker here. But, oh, thank you. So this is on demand, lazy evaluation, right? He didn't give it to me earlier, so only on request. Clever, that's great. So at this point, of course, I've got a third one, a little bending, but nevertheless. And you got this lazy evaluation. So you can see how we accumulated these functions right here, and we are holding on to it. What work did it do? Absolutely nothing. And it's waiting. And if you came back and said, you know what, never mind, it's like, gosh, that's great, I didn't do any work. On the other hand, you said, go run this code. That's when it's going to evaluate through this and run through the sequence of this call. And so that's pretty much lazy evaluation, how that works, thanks to these markers. So the point really is, how does this actually work? Let's understand this. When I run this code, here's another thing to think about. Here is the little thing to focus on. Imagine these are your 2 feet and you're standing on top of that. It's kind of like you're standing on top. And what you have is, you're going through these steps. Here is what you're not doing. You're not taking an entire collection. Imagine this for a minute. And don't stand up when I say stand up, so I'm just making an example. Suppose I were to say, in this room, I want only people wearing a t-shirt to stand up, and the people wearing a regular shirt should be sitting down. What's going to happen? We're going to hear a rumble, and people wearing a t-shirt are going to stand up, and those wearing a regular shirt are going to be sitting in. And then I'm going to say, if you're wearing a black color shoes, continue to stand, otherwise sit down. We're going to hear another rumble. Well, these are eager evaluations. And when you're done with all of that, I'm going to say, I want the first person, please. And everybody else is like, damn, Why did he make me move all this time if you only wanted the first person, right? Well, instead we can do a little differently. I could say, hey, are you wearing a t-shirt? Yeah. Is your shoes black color? No, sorry. What about you, sir? Yep. So we got our winner. We are done. Notice what I did. I went through the first function. Are you wearing a t-shirt? He said yes. Are you wearing a black color shoe? He said no. Done. I might have other things I don't care at this point. Move down to the next person. Hey, t-shirt? Yes. Wearing a black color shoe? Yes. I could go on to ask a few things. Are you wearing glasses? He says no. Sorry, I want to move on. So I could be doing this until I find, are you wearing a shoe at all? Yes, he is. Black color, okay. T-shirt, wearing a glasses. We got our winner, right? So the point is, I am not going through an entire collection to get a new collection, because that would suck. We would be producing a lot of garbage, executing a lot of effort, and that's a wasted performance. Instead, we come to this and say, let's take the number 1 and we'll drop the number 1 through this. And 1 says, I'm really sorry, I'm not cut out for this, and runs out through this door, right? Because 1 is not greater than 3. It's like, darn it, we lost 1, let's try 2. Same fate for the 2, it ran out. What about 3? Same thing. Now we say, what about 5? 5 says, oh yeah, I'm greater than 3. There's a little bit of hope. Great, let's go to the next level. What about being even? And 5 says, I'm sorry, I'm not even. What about 4? 4 is greater than 3. 4 is even. Let's double 4. Find first. And find first says, hey, thanks. Hey, that's it. We don't have to do any more work. And if you notice the sequence in which the code executes, let's take a look. Output is greater than 3 plus, let's say, in this case, number. And I'm going to output is even, and I'm going to say number. And finally, over here, I'm going to output double it plus number. Before I run, I want to emphasize one thing. This is just a stupid example. This is a side effect. We should not be doing this. So just keep that in mind. I would never do this in production code, right? So the point is, they all have to be lazy. You cannot produce output. Ideally, I should have put a debugger and stepped through the debugger and showed you, but I'm too lazy right now. Hey, I'm lazy. Okay, so let's go ahead and run this code and see what happens. Notice it evaluated 1, then 2, then 3, then it evaluated 5, then it evaluated 4, but it never ever touched 6 or anything after the variable 4 because it found its solution at this point. That's a lazy evaluation right there working. To make this a little bit more effective, let's try this a little differently. I'm going to remove this print statement, and at the very end of this statement, I'm going to go ahead and say output, end of that expression, I'm going to say output, done. I run the code, you can see all that evaluation followed by the word done being printed. That's great. But I'm going to come back here, and I'm going to stop just shy of the very last call. So notice, I went through the filter and the map, but I did not come to the find first. So what did we just do? We said, filter please, and map. It says, okay, I'm ready. What do you want to do? Nothing. So like, oh, okay, I'll go home. So it doesn't really do any evaluation. Here's another way to relate to this. You probably have seen people at work who are like this code. You know, one of the dude you have at work, right? What I'm talking about, comes to work in the morning, looks around and says, hey, where's the boss? You say, oh, the boss is sick today. Yes, I don't have to do any work. So when you run this code, notice, it just printed done. It never actually evaluated those functions because it's lazy. So even though we built up that pipeline of functions to evaluate, it simply said, I don't have to waste my time and effort running through this pipeline because after all, you're not executing it. And so it just throws away, and it did not evaluate any of those. So the processing time that it's going to take to evaluate through this is completely gone, as you can see. So far, so good? Any questions or comments? Don't be too lazy about it. You can ask questions eagerly. Most welcome to ask any question anytime. Don't hesitate at all. So we saw how laziness can play a nice role in what we do. Well, okay, Now, I mentioned a few things, and I want to reiterate a few things before we go any further, because I think it's important to think about these things. First is immutability. So what does immutability really mean? Immutability means you are not going to modify a variable once you create it. And in functional programming languages, functional programming languages enforce immutability. You cannot change variables once you create them. An example in Haskell, for example, if you go to Haskell and say, here's a variable, thanks, but you cannot change this anymore. So variables really are like values. What about imperative, hybrid languages? Here is an example in Scala, for instance. Val, I'm going to say x equals 7, and I'm going to print the value of x, and you can see that in this case, the value of x is 7. But I'm going to say x is 22, and I'm going to print the value of x. Notice Scala immediately gives me an error saying, are you kidding? You cannot modify the value. Hey, why not? Because I declared it as a val, as you can see. So what is a val? Val stands for immutable. However, unfortunately, Scala is also a hybrid language, which means you can say var. Now that I change the val to a var, you can see when I run this code, it does allow me to change the value from 7 to 22. This is a mutable variable. If you ask me what is var, var is actually called the keyword of shame. Because if you use var, you cannot make eye contact with your colleague for the rest of the day. You only look at the floor and walk, and they will look at you and say, you mutated it, didn't you? It's like, yes. And they will follow you to your desk and refactor your code. So the point really is, you don't want to be mutating stuff around. It really makes concurrency really hard. Reasoning code becomes hard. A lot of those reasons. So you definitely want to favor immutability as much as you can. And of course, purely functional languages like Haskell, and even so, languages like Erlang really make it almost impossible to modify variables once you create it. But languages like Scala, you got to be a bit careful. In Java, you have to be even more careful, because in Java, unless you mark a variable final, it becomes mutable, and you got to be a bit more careful about it. But having said that, immutability is pretty important. But with immutability, what happens? Immutability paves way for one thing, which is pure functions. So what is a pure function? A pure function is a function which has no side effects. So what is a side effect? A side effect is where you call a function and it changes stuff around it. These are called naughty little functions. Because you call the function, it's kind of quietly walks over and you say, you did something, didn't you? And now you have to figure out for the rest of the day what it changed. And we call it debugging, right? And it's really horrible, and eventually discover what it went around and changed it. So there's two things to consider about pure functions. It does not change anything. So that's the first thing, change anything. But that's not enough. It's not enough that you did not change anything. There's something equally important. It does not depend on anything that changes. Now, this may be a little steep, but this is extremely important. You are not a pure function just because you didn't change the world around you. You shouldn't depend on anything that changes also. If you like to put this in a more philosophical term, see no evil, do no evil. Both, right? So it's not enough if you say, I'm not doing anything evil. Not stopping evil is also evil, right? So this is both. See no evil, do no evil. Well, do no evil is the first one. See no evil is the second one. So meaning, don't mutate and don't watch anything that's being mutated. Now you may wonder, gosh, this looks like really steep. I can understand fully why this is important. Why? Because if I am not pure, you call me, I leave a residue behind, which means it matters whether you call me or not, because by calling me, you know that I did something, and if you didn't call me, you won't see the change, and you would know that I'm working or not working. But why in the world are you so upset about the world around me not changing? Well, the reason is, if I am eager, you say, Venkat, what's the time right now? I'm going to say, well, the time right now is 7:30 p.m. Great. But let's say I'm lazy. And you say, what's the time, Venkat? I'm going to take my sweet time, scratch a little bit, maybe sip a cup of coffee, and then I'm going to say, what? Well, it's too late. The time has moved on. So the time is ever changing. And if you ask me what time is, you're going to say, fast now. Tell me what time is now. I don't want you to tell me tomorrow what time it is now, right? So I'm not changing the time. I'm not that good, right? I'm just following along. The time is changing. But I can notice what the time is, but that's impure. That makes me impure. So in other words, if a function has to be lazy, you cannot push it and say, are you running now? Can you run faster? And the function says, I may run, I may not run, I may run later. What's the hurry? You're like, hurry? I'm waiting for that variable to change. You better run now. Sorry, that defeats the purpose. So that's the reason why you cannot have mutability in pure functions. So we saw what a pure function does. But what does a pure function give to us? It gives us some enormous benefits. The first benefit is the function can be lazy. You cannot imagine a function being lazy if it is not pure. In other words, impure functions are condemned to run eagerly, right? So they have to run all the time eagerly. Lazy functions, pure functions can be lazy. But there are other benefits that pure functions can give also. We don't have to go into them, but laziness really comes directly out of the purity of functions, so that's something very important. Now, in the case of language like Haskell will enforce that your functions are pure. In my personal opinion, Java is better than Haskell for this reason. Because Java doesn't enforce. It does something even better. It assumes. And I love languages with assume. Because if it assumes and you don't agree with it, you know who's going to win. The language does. And the result can be a disaster. And that's why I like languages that assume things. Because you get hurt once, and you live with that scar forever, and you would never repeat that error. Right? So there's no compiler to support you. So the language says, don't ever mess with things. So to understand this, let's take a look at a quick example to see why purity is so important to keep in mind. So let's say for a minute we have this collection of these numbers, and what I want to do here is I want to simply iterate through, and I want to print a result here. So I'm going to say stream, and in this case stream of integer, and I'm going to say stream is equal to, and I'm going to go ahead and create at this point numbers dot stream, and I'm going to say, given these stream of numbers, I want to ask it to say dot map, and given an element times factor, and then I'm going to simply store that into a little variable. And now I'm going to say right off the bat, I'm going to say stream dot for each system dot out, and I'm going to print it. Well, let's start with this little example for a minute, and I'm going to go back here and say, in this particular code, I'm going to say int factor is equal to, let's say, 2. So when I run this code, you're going to see that in this particular case, it's able to produce the result for us, which is times 2. Well, that seems to be working really nice for us. But I want you to look at this for a second. Now, when do you think this function is evaluated? On what line number, if you were to look at line numbers, it's going to run this particular code? That's correct. It's going to run on line 14. Now, notice I said E is E times factor. I come along and say, well, okay, step back for a second. If you were programming in Java 7, you would have said final over here. But Java 8 says you don't have to put final. Now you may wonder, why don't you put final? I got a reason for it. You've been putting final for such a long time. Anybody likes declaring these final? Nobody. So Java comes to you and says, Java says, you know what? You and I have been going out for 20 years. We can trust each other just a little bit. So it gives you a little benefit of doubt, right? We've been going out, we've been nice friends. We don't need this formality between us. I trust you. You're like, thanks, Java. And so you can just do without final. But you come along and you say, factor equals 4. Immediately, you get a compilation error. And Java says, I thought we had an understanding, right? And it says, how could you do this to me? You changed it, right? It's like, I'm sorry, didn't mean to do that. So go back and put final now. So you broke the contract, the understanding that you had, right? So that's basically what it is. And why does Java do that? Well, Java does that because Java wants to make sure our little closure here is actually pure. So that seems like a great idea so far. Hey, this is awesome. I like a language that protects me. Not so fast. Because you know, when you tell no to a programmer, there are some programmers who would say, okay. And there are other programmers who would say, let me see to it, right? And they roll their sleeves and they get to work. So here's one idea. I could put a little square bracket, and I could say new int square bracket, and then you put this into an array, and then you come back here and say square bracket 0 to access it. And now you say, aha, I'm going to say factor 0 equals 77. Let's even make it -2. Now what do you think is going to happen? Well, Java tried to protect you a minute ago. Java looks at this code, shakes his head and says, you cannot be fixed, right? And it just walks away and compiles the code. Now the question is, what's going to be the output? Well, remember how this factor came in here. So how many of you think this is going to be the values multiplied by 2? That's good. How many of you think it's going to be negative? This is even better answer, because you know what happened just now. Some of you said it's going to be negative, and rest of you thought, I don't have a clue. Because you didn't raise your hand for the first question, you didn't raise your hand for the second question. So it's only a third category, right? I don't have a clue. And that's exactly why this is such a bad idea. Because if you have to think and reason, that's a reason that this is a bad idea. And yes, it was negative, which is really not good. But this can be even worse. It depends on when you are changing this, and depends on when this is being evaluated. Imagine you're in a parallel stream or multi-threading. Gosh, that could be more debugging for us to do. So this can be really treacherous. And that is the reason why you want to really make sure this is pure. Java assumes it's pure beyond a certain level. And if it's not pure, what does it say? It says, you know what, it's your problem. And that compiles the code and goes away. And what will happen when you run the code? That's the beauty. You have no clue. And every time you run, you may get a different result. And then it's going to be really, really a long night to debug. So we don't want to do that. So you want purity from lazy functions. But given that it's purity that we really want from these, let's take a slightly different example and work through it. I'm going to say, in this case, find the total of square root of first k numbers, k, let's say, prime numbers, let's say starting, so k prime numbers starting with n. So I got a little value n, a little value k, and I want to do this. Well, but how would I go about solving this particular problem? I'm going to write a little function here, a boolean is prime, and I'm going to take a number as a parameter n, and all I'm going to do with this number given, we'll call it number, and what do I want to do with this number? Well, all I'm going to do is simply say return number is greater than 1, and we'll say int stream dot range, and in this case I'm going to say range value of 2 to the number, and we will simply say dot none match, and in this case we're going to say given an index I, number mod I is equal to 0. That tells us if a number is prime or not. Great. But the real problem is down here. I want to find the square root of the first k numbers. So let's go ahead and write it. Output compute, and I'm going to give a value of n. Let's say this is going to be 100, and I'm going to give another one which is 49. So I want to find the square root of all the prime numbers in that range. Well, how would I implement this? Public static, let's say double, compute, int n and int k. So let's do this in the way we are so familiar with. So what would we do? Well, double result is equal to 0 to begin with. Return result, right? This is called hope. So we'll get to the result and return it, right? Great. But what would I do in between? You will first say int index equals to n, while, we'll come back to that, if index is prime of index is greater than, is equal to true, then what do? You say in that case, a result plus equal to is going to be math dot square root of index. So seems reasonable, isn't it so far? Are we done? Oh no, you have to increment the index. Oh, of course, I got to increment the index, so I will increment the index right here. What do you think? Oh no, you shouldn't increment the index there. Where should I do it? You got to increment it here. Oh no, that's too far, here. Okay, all right, are we good? Maybe. Well, but we're not done. What about the while loop? I'm going to say now int count equal to 0. And what would I do here? Count is less than k. And you pause for a second, don't you? And you ask yourselves, is it less than or is less than or equal to? Do you ever ask this question? Every single time. And the day you don't ask it is called the national off by one error day, right? And you get bitten by this so hard. And you finish it, you move on, but what do? You keep turning back and staring at it, right? And then you come back again. And then you go on. And then that keeps nagging you, isn't it? And you're a little nervous. Then you realize, I better increment the count. So count plus plus. Are we done? No. Because you shouldn't increment the count here, you should do it here. Now you show this code to somebody and say, what does this code do? And they ask you, where's the bathroom? Right? Because this is giving them all kinds of things in their stomach, right? And this is really horrible code to work with. In the meantime, what is going to happen? The business analyst, you know how cute they are always, because they want to know what we are doing. And the business analyst comes, sits next to us and says, hey, what is this code doing? And you tell the business analyst, that's what I'm trying to figure out, be quiet, right? Because it's so confusing, we don't have a clue ourselves. Well, okay, we wrote this code, and we run the code, it produced some result. Don't even ask me if this is right. Okay, it did some work. But you can see how complex that piece of code is. But we definitely want to write this in a lot better way. Let's see how we can write it. What am I going to do? I'm going to say stream dot iterate, starting with n, given a value e plus 1. Just stare at that for a minute. What in the world is that? That's an infinite stream. So we are looking at a stream that is absolutely boundless. It is an infinite stream, and the infinite stream says, I will start with the value of n, in this case 100 when you call it here, and I have absolutely no limit. So 100, 101, 102, 103, 104 keeps on going. Now you look at this and say, oh my gosh, if this is infinite, where would you store it? On the cloud, of course. So the point really is that this is an infinite stream altogether, right? So given this infinite stream, but it's very smart, it's going to be lazy valuation. So it says I will not compute anything until I have a demand for the value. Well, that's great. I've got an infinite stream on my hand. Now what would I do? I'll say dot filter, and in this case I'm going to say sample, and I'm going to say is prime. Hey, only go from an infinite stream of numbers to an infinite stream of prime numbers. Great. But I want to perform a map operation, and I want to say, given a sample, I want to perform the math actually, and square root operation. We transform this, and I'm going to say, in this case, map to double, because I can use an easier operation a little bit later. But then I'm going to say dot limit, and what am I going to say here? K. Did you notice? Not less than k. Not less than or equal to k. It's k, damn it. Put it and move on, right? There is nothing to really sit there and stare. It becomes highly expressive. And then, of course, you're going to say some operation I want to perform, and you get the results out of it. And of course, I want to return this, so I'll simply say return that result that we have on our hand at this point. So you can see how expressive the code has become all of a sudden. So you said, given an infinite stream, I want to filter all the prime, get the square root of them, and then only get k of them and total them. So that it becomes extremely expressive code, which produces exactly the same result as the previous one, almost, Yeah, and of course, in this case, it was a 1 in the end, right? Yeah. So, yeah, a little inaccuracy, but now we have to figure out which one is more accurate. So the point really is that you can see in this case, this is very highly expressive. Did you notice, if you put this code in front of people and say, I said, they're going to oscillate, but look at this code. It's a one pass through the function. Collection of all numbers, filter them, double them, get me the square root of them, limit to k values, total it, you're done. And if you look at this code, the code is extremely expressive. We can praise this code a lot, but the real praise here goes to laziness, because you could not have done this without lazy evaluation, right? So lazy evaluation makes this possible. So we saw this earlier. So what's the benefit of being lazy? Well, the first benefit of lazy is you can have more fluent code. So fluency comes in. It is also more efficient. You saw that earlier. So efficient code comes through it as well. The code is more fluent. It's more expressive. We saw that as well. And then, of course, the code is more efficient. We saw that in the previous example. So we got a little bit of an efficiency backed in, but this could not even be imaginable if this code was not making use of laziness. So laziness is extremely important. And so this evaluation is lazy right here. This evaluation and this one, and including limit, is lazy. Limit says, I'm going to let k values go through. How many have you let go through? None, because nothing came through yet. I'm not going to be eagerly evaluating it. I'll wait for stuff to come through and work on it at that time, right? So it's going to be very lazy in its evaluation. And what triggers all this computation? Sum is the terminal operation, and sum is the one that triggers all this evaluation and kicks in for evaluating only for as many times as the k, as the limit says. So we saw how we are able to use the infinite stream and produce the results out of it. So we can produce these kinds of sequence generators very powerfully in code, and that gives us way to work with some very fancy structures. Now, this is where things get a bit more interesting. When you begin to use lazy evaluation, you quickly realize, we can take these lazy evaluations and we can turn problems from eager evaluation to lazy evaluation. This can be very useful in a lot of different settings. If you're going through a search algorithm, you can say, I want to do all the search right now, or I can postpone the searches until a later time, and I can do the search only on demand. And as a result, you can automatically make it very efficient, like you saw in looking for the value, the find first, for example, things like that. But I want to show this to you in a slightly different light, where we can actually use this lazy evaluation in something that you don't really think about too often. So let's think of the lazy evaluation in terms of tail recursion. So what is a tail recursion? Well, tail recursion basically is when you are not going to expend the effort of walking the stack when you are calling methods. Let's look at an example of this real quick. Suppose we have a call to a factorial for a minute. So I'm going to say output, so print line here. Actually, I want to do this in Scala. So let's say I want to print line factorial of, let's say, 5 over here. Well, I want to write the factorial, so I'll say define factorial, and the factorial says, given a number, I'm going to return an integer, a big integer, and the result of this is going to be, if n is equal to 1, return the value of n, else return n times factorial of n minus 1. So a very simple recursion, as you can see right here. Now, if you look at this code, it's a very simple recursion, and one of the cool things about recursion is everybody loves recursion, isn't it? Because recursion is where you can solve a problem using solutions to the subproblem. And when you start using recursion, you have more friends with you. They want to hang out with you because they think you are cool, right? So you have mastered recursion, you're having a great time, but there's one person always there who doesn't like you and comes to you and says, so you think recursion is cool, huh? You say, of course, how could recursion not be cool? Because you're having this recursion party one night. And at that time, this dude comes over and says, if recursion is so cool, why don't you try this, huh? And what's going to happen when you do this? Well, it gives you a Stack Overflow. the party is over, right? Everybody left, and they said, gosh, this sucks. We thought you were really cute, but this is not good at all, right? And the party is over, and we sit there staring at this. My gosh, recursion is so cool, except it doesn't work when it's really a deep stack, right? So how sad that is. Well, thankfully, we don't have to go through that pain. This is where a fantastic book comes in. It's called SICP. If you just Google for SICP, you'll find it if you have not found it already. And this is for structure and interpretation of computer programs. And this book by Sussman and Sussman talks about various wonderful things. It's a bit scary actually, because this is a book they use in the first level of MIT courses. It's unbelievable what how they torture these people. But anyways, this book talks about some really interesting concepts. And one of the things they talk about is a thing called procedure versus what's called a process. A procedure is the code you are writing. A process is the code that actually runs. We all know the code we write is not the code that runs. Your compiler compiles the code, then there's an optimization that kicks in, and eventually an optimized code runs through the execution. So they talk about a procedure versus a process, and the idea behind this is if you write an iterative procedure, you run it as an iterative process, no surprise there. If you write it as a recursive procedure and you run it as a recursive process, no surprise there, except that it blows up the stack and fails. But the real power is if you can write it as a recursive procedure, but quietly it will run as an iterative process. So compiler techniques can be used to quietly convert a recursion into an iteration. Well, the benefit is a recursion will blow up a stack if it walks the stack, but an iteration will not blow up the stack because you're in the same stack just iterating and working through the values. So tail call optimization, also known as TCO, is simply to optimize the recursion when it is in the so-called tail call position. So if you look at this code for a minute, stare at this and say, what's the very last thing you do in this highlighted code? That's correct, it's a multiplication. You are absolutely right. Sometimes people look at this and say, oh, it's factorial. Well, it kind of confuses sometimes, but it's multiplication. So what that means is you're saying, I've got a variable n on my hand, I'm ready to multiply, but no, I can't. I got to wait. So you leave this variable on your stack and you climb your stack one level up. And on the second level stack, you got n-1 and you climb the stack again and again and again until you blow up the stack or get it done. Well, we can change this a little bit now. So what we're going to do is we're going to say, hey, rather than doing this, let's pass the factorial as a parameter to this function. So in this case, I said factorial of big int, and we are passing that over here as a value. And now we are saying what I want to do with this function is if n is equal to 1, I want to return the fact value itself. On the other hand, if n is not equal to 1, then I'm going to call factorial, but I'm going to do a preemptive calculation of factorial times n and pass n-1. So in this case, what is the last operation we perform in this function? It's the call to factorial. That's what is called the tail call position. So tail means that's the very last thing you do. Now look at the beauty of this. A compiler can be smart enough to say, when I come to the very end, rather than calling that function, I will step back and recall the function with a different parameter so it can turn itself into an iteration rather than a recursion. So it can optimize that very easily. So now if you go back and try this out, you can see in this case it gave the result properly, but if you try that large value that your buddy of yours who doesn't like you and recursion gave the value, you can run it and you can see in this case it produced the result. And you can ask that person now to memorize the result, right? And the point really is that you can see that there was no more error. Well, this is great so far, except for one small problem. For this to know it is a tail call optimization, it looked over here and said, aha, you're calling in tail call, I figured it out. You can also do a few other things in Scala. You can say scala.runtime.tailrec, And there are annotations you can use for this particular call, and you can ask it to run through those things. It's probably in another package, but you can call these particular tail rec calls, and you can ask it to run through some of these values very easily. But nevertheless, the point is it's a function. But what if life is not that simple? It never is. So what if I have a process function, and the process function takes an integer value, and all I'm doing is calling, in this particular case, I'm going to call, let's say, consume, and I'm going to pass the value of n. But I'm going to say if, let's say, n is equal to 1, return 1, otherwise go ahead and call the consume. This is a silly example I'm going to write to illustrate the point. Well, okay so far, but what about the consume function? The consume function says, when you call me, well, obviously in this case, I'm going to return the result as an integer. So the consume function says, when you call me with an integer, I'm going to now say return a int, and all I'm going to do is simply turn around and call process with the n minus 1. Well, let's try this. I'm going to print line here. I'm going to call process, and let's send a value of 5 over here, and it gives you a result of 1. That was pretty quick. Well, but what if I were to call a fairly large value? Well, in this case, you can see when I call this with a fairly large value, you're going to see that it's going to blow up the stack pretty quickly. Now, why is that? Well, the reason is process is calling consume, and consuming is calling process, and the compiler says, hey, one function is calling another function. They're kind of independent of each other. There's nothing to do with tail call. But this actually is a tail recursion, except that you're making one intermediate stop and you're going like this back and forth. Well, they couldn't handle it, but at least they gave us a really good name. It's called trampoline, meaning you can't use it, right? So trampoline simply is like you're on a trampoline and you can jump on a trampoline. I've never seen anybody jump like that on a trampoline and survive, but that's kind of trampoline, right? You can jump on it. Well, this is called a trampoline trail recursion, but of course in this case it doesn't handle it, it blows up the stack. What can we do? Well, this is where laziness can come into picture. So it's an application of laziness. Notice what I'm going to do. Rather than calling consume, why don't you return a lambda, and then when you return a lambda, the caller gets a lambda, and they can decide whether they want to call or quit with the result. So they can examine the result. If the result is really a result, they can return it. Otherwise, they can call it back, turn it into a recursion. So to do this, Scala already handles this. So I'm going to bring in an import statement right here. So I'm going to go ahead and import right about here. Let's say import of the tail calls. The first change I'm going to make is a tail rec. So I'll say tail rec. And in this case, it's going to be an integer of tail rec I'm going to return. So this is going to become just a tail rec object that I'm going to use for this particular purpose. Likewise, this becomes a tail rec that I'm going to return. Well, obviously this is an object, but this object is going to store a lambda rather than holding a result at this point. Well, I come in here. If the n is equal to 1, what am I going to do? I'm going to say done of 1. Meaning, I'm going to return to you a result wrapped into a little object, and you can query that and say, are you done? Oh yeah, thanks. I'm going to return the result and not call you back. On the other hand, you can come here and say call, and you can then pass that to the call object. The call object basically says, it's a tail call object, and it basically says, I'm going to go ahead and make a tail call, wraps that function in and says, I'm going to go invoke that particular call function right now. So that becomes really a lambda to invoke very comfortably for us. Well, how does this really help us? Well, the point really is, when I run this, notice what it returned. It didn't return a 1, it returned a done. Likewise, notice it's a done 1, but if I say 5, whatever that large value is, notice the result this time is call function and not a done. So it's returning a lazy evaluation. It didn't do any real work yet. It simply gave you this lambda and said, hold on to this, we'll talk about this later. And you're just holding on to it, it's like, what do I do now? Well, remember one other thing. If you wanted the result, you have to call something else. What is that? The terminal function, that's correct. Other day I asked this question, somebody said call daddy. No, that's not what I meant. So you got to call the terminal function, right? So dot result, and I'm going to say result, that's a terminal function. Notice it gave us a done a minute ago. Now it returns a result, as you can see when you called it. Likewise, when you go back here and say 50,000, whatever that you wanted to call, and I say dot result over here, you can see it snaps back with the result very quickly. So that shows you how it can evaluate it on demand. That result is a terminal function that triggers in computation and gives you the result of it. So we saw how we can use some of these concepts to gain quite a bit of efficiency in code. So the moral of the story is this: lazy evaluation can become extremely beneficial to us. Laziness covers a lot of grounds by hiding a lot of details in the code, and when you write code like this, you can see how elegant this is. But in reality, this code would not work if this was evaluated eagerly. So laziness makes this fluency possible. We also got elegance in this code. We got efficiency because it postpones evaluation and evaluates things only on demand, only when it has to evaluate, and that's one of the benefits you get. So with laziness, we can begin to really write our code in ways we can make it more efficient. So when you want laziness, how do you gain laziness in languages like Java? Well, rather than receiving a value, you could start receiving lambda expressions. For example, let's say I'll just show you, wrap up with the one example here. For instance, if I have a function, let's say evaluate, we saw this earlier, evaluate, and in this case you saw how we received a value. So we'll circle back to the first example we saw. So I got a value coming in. Actually, I want to change it. Let's go ahead and write a function called evaluate. So in this particular case, I wanted to call the evaluate function after all. So let's go ahead and say evaluate, add, let's say 1 and 2. And in this case, you know, when you call evaluate, you can say public. Let's say static, this is going to be int evaluate. And this takes a value, and simply in this, it says return the value that was passed in. Well, you can see now, we saw this earlier, and I'm going to provide this function, let's say add, which takes op1, so it's say op1 and op2, and of course we're going to return op1 plus op2 here. But I'm also going to put a little statement here so we can actually see it run. We'll say called. So as you can see, when I run this code, it is going to call the add method, so we can see that clearly that add was actually called, no doubt about it. On the other hand, I really wanted lazy evaluation, meaning if I change this to a 42, we didn't reap any benefit, as you can see. What a sad story. But here's what I'm going to do instead. Rather than receiving a value, I'm going to change this to receiving a supplier. So I'm going to change it to a function, and I'm going to say this becomes a supplier of integer, and I'm going to say value. And within here, I'm going to say return value.get, as you can see. Now I come back to this code, and I'm going to change this to a lambda right away, and you can see it called this function, and it produced the result as we would expect. But if I come back and refactor this code, and I'm going to say something along the lines of if, maybe there's two values we are receiving, let's say for a minute, int, let's say v and this, and I said if v is greater than, let's say v is greater than 5, return this value, and I'm going to say else return, let's say a value 4. Well, I can come back here and call evaluate, and in this case, of course, when I had an eager evaluation, you know it evaluated all the time, but if I were to say the value is 6, you can see that it's evaluating it. But if I say the value is 3, notice in this case, it never evaluated that function. So in other words, you can put a lambda expression, and then by putting a lambda expression, you can eliminate evaluating the call. You can be lazy. But I want to conclude by saying one thing, which is my favorite quote ever, because this has changed my life. I remember this even in what I do every single day. This is a quote from David West, and I think it is probably one of the profound quotes in computer science, in my opinion. David West said, in computer science, you can solve almost any problem by using one more level of indirection, which is exactly what we did here. Rather than passing a value, you passed a lambda, which will eventually compute the value. And I think of this almost every day when I code. When I'm stuck with a problem, I immediately invoke his words and say, what's the level of indirection I should be using here? I think that's a very profound way to think about it. In computer science, we can solve almost any problem by using one more level of indirection, and lambdas give us a level of indirection, and that nicely leads to laziness. I hope you found that useful. Thank you.